Okay, so here we go. Idea number one. Does this shape mean anything to you? How about now? For a long time I've been fascinated by the internal structure of the Khufu pyramid. It's one of those great mysteries of the world, I suppose, how they were able to construct such an enormous building in some reasonable time frame. We're not exactly sure how long it took, but one thing we are sure of, it's there, and we're still not really sure how it was constructed. There are a lot of theories, some of which could be resolved if we could only stare inside the pyramid and find out more about its internal structure. We have done some gravitational studies over the years and various seismic attempts at reconciling what's inside the pyramid, but I had what I thought was a fairly unique idea of how we might be able to peer inside the pyramid using cosmic rays. Oh, please excuse the crudity of this model. I only just threw it together tonight and I couldn't paint it or anything, so red straws it'll have to be. Okay, some numbers about the pyramid itself. There's approximately 2.3 million blocks. It's about 146 meters tall. It's currently 130 something, about 139 I believe, due to erosion over the eons that it's stayed up there. It's about 230 meters per side, and it weighs about 5.9 teragrams, which is a heck of a lot when you think about each one of those blocks had to be moved in place by nothing but human power. They didn't have cranes as far as we know, although there are some construction theories that posit that they had primitive ones. There's various ideas that maybe they used ramps and just simple wedges or rollers, things like that, to move this enormous amount of 2.3 million blocks over maybe a 20 to 50 year period. Even if it was 200 years, it's still quite a miraculous construction for the time. Alrighty, so looking inside it and using cosmic rays to do it. First of all, we need to talk about cosmic rays. Cosmic rays are a natural form of radioactivity. We're not entirely sure how particles end up with such high energies, but we believe it may have something to do with black holes or supernovae, etc., or perhaps relic particles left over from the Big Bang. But the great majority of them, about 90%, a little bit less than that, are hydrogen nuclei, protons. About 9% are helium nuclei, and about 1% of them are electrons. There's some tiny fraction, much less than 1%, that are heavier nuclei and ions, but we're not completely sure why electrons figure in such small amounts in cosmic rays. You would think that they would be up there with hydrogen, or their energy spectra is not consistent with various models, and there's some interesting research going on into why that's the case. It may have to do with a very different mass, but anyway, that's a subject for someone who's far more skilled in that art than I am. One thing to know about cosmic rays is some of them are very, very energetic, and actually the great majority of them give our colliders here on Earth a run for their money. On average, they are about 3 gigaelectron volts. The most common ones range from about 10 megaelectron volts to 10 gigaelectron volts. So that's 3 orders of magnitude spread there just in the kind of energy spectra of the most common ones. The particles of that energy are extremely penetrating. When they enter the atmosphere, they collide generally with nitrogen or some other atom in the high atmosphere, and they generate pions. Pions then decay fairly quickly into muons and neutrinos, but the neutrinos are so penetrating and so weakly interacting we don't see many of them except with very, very large detectors, and then they're obscured by more common sources of neutrinos like the Sun. But the extremely energetic muons that are produced, muon's kind of like a heavy electron, and they come in particle-antiparticle versions, so they can have either charge. But they're very, very energetic, and they can go up to 4 kilometers into the ground. That's how energetic they are. So a couple of meters of lead and a couple of 100 meters of rock, not going to stop them, not going to slow them down that much, although they will scatter off normal matter, and we'll talk about why that could be useful for our particular purposes of imaging inside the pyramid a bit later. One thing about cosmic rays, it's still a little bit mysterious, but there are various models to explain it. It's this thing called the GZK cutoff. GZK is the initials of the scientists that calculated it. I'm not going to try and pronounce their names because I'll probably get it wrong. But essentially it posits that there's a limit around 5 times 10 to the 19 electron volts where we shouldn't see very many or ideally any cosmic rays above that energy level. Although we do see extremely or ultra high energy cosmic rays. You might want to Google the the oh my god particle for information about them. But basically the GZK cutoff works because as the protons are zipping along, because they're so close to the speed of light, the cosmic background radiation is extremely blue shifted as far as they're concerned. And it actually comes up to where there's a reasonable cross section where they will interact with a cosmic background radiation photon and scatter off it, reducing their energy back down to a more realistic number. This suggests that there's about a 50 megaparsec horizon, which is 116 million light years, I believe, if I did the math right. So we do see a fair amount of extremely energetic sources within that area, but not enough to account for some of the numbers that we see in the ultra high energy cosmic rays. And this is a bit of a mystery, although there has been various mechanisms suggested, and perhaps the other possibility is that at really high energies, even relativity might be a little bit wrong, and there's ideas about doubly special relativity and things like that to deal with this observation that the GZK cutoff is not respected, although it could just be experimental error, although looking at the latest results I don't think it is, and there's some new science there perhaps for someone. Okay, so how do we detect cosmic rays? Cosmic rays are pretty much like any form of ionizing radiation. They can produce ions when they interact with matter. So the most common particle detector you'd find is a Geiger counter. For example, this one that I built some time ago. This uses a Russian pancake Geiger tube. Inside is a low pressure neon gas with a little bit of bromine in it, and you apply a high voltage across it and it will count with each ionization that occurs as a particle passes through it. You can hear it clicking away here with this background radiation. Some tiny percentage of the clicks that this thing produces just sitting here counting background radiation is cosmic radiation, but the cosmic radiation interacts very weakly with this kind of detector because of it is essentially a very low pressure gas. There isn't a whole lot of matter in there, so the chances of a cosmic ray zooming through this thing, interacting with one of the gas particles, or one of the particles, maybe the metal or the casing around it, to generate an electromagnetic cascade that would trigger the detector is very low. So most of these clicks are actually radiation from nuclides in the surrounding area. I've got some potassium and some americium, and obviously I'm inside a concrete structure. It's full of all kinds of radionuclides, so there's all kinds of decays going on, and even those are very weakly interacting with the detector, but there's a significant amount of clicks, as we can hear here. The background's about 25 counts per minute for this particular device, so about every 2 seconds it clicks. So how does it actually work? Inside, a high energy particle comes in, generates some ions. There's a strong electric field between one electrode and the outer wall if you're using a tube, or in this case between the circles of metal that you saw on the top of the detector and the cup bit underneath. This separates the ions, and they gain a lot of energy as they fall across this potential difference. They smack into other atoms and they ionize them as well, so you get an avalanche reaction that causes a cascade of ions and eventually, essentially, a discharge. This whole device could be, seen as a capacitor, so it has some capacitance. And this breakdown of the gas, Townsend avalanche I believe it's called, causes the capacitor to discharge, and you see a pulse produced across the resistor that biases it. The small amount of bromine or other halogen gas that's in this particular kind of tube helps to stop this runaway after it's discharged the tube. If you didn't have that in there, if you didn't have or some external circuit to allow quenching of the arc, the thing would destroy itself. It would just short out the power supply as soon as it fired the first time. There's a lot to be said about this, and I won't cover particle detection too deeply in this particular video. Let's go on to scintillation now. Scintillation is a far more efficient method of detecting particularly high energy particles because, as I said, they interact so weakly with gas detectors. Scintillators, there's a heck of a lot that we could say about scintillators. The physics of scintillators is fascinating, and exactly how the radiation gets turned into a pulse of light and how to couple that light into a detector efficiently is a truly fascinating and enormous subject, and I recommend you read about it if you're interested. It's really quite interesting. Essentially what you have is a block of matter, transparent, particle passes through it, and it produces a flash of light when it interacts with the detector. You could, although it's not true Cherenkov radiation, you could consider it a kind of braking radiation. Essentially the particles travelling very fast through the crystal lattice produces a shock wave, kind of like a supersonic aircraft passing through air. That shock wave then couples to certain dopants that you put in the crystal to produce light at a useful frequency, generally somewhere in the blue end of the spectrum, and that light comes as a cone in the direction of the particle travelled through the detector. So you can actually put multiple detectors around one crystal, and you can do some interesting things like that. The detectors generally used are called PMTs, photomultiplier tubes. I have one here. This is a side-looking PMT. They're a kind of vacuum tube. They're called photomultiplier tubes because they multiply the current produced by photons interacting with the metal in the metal plate inside. They're called dinodes. Each of these you can see around here is a little cup-shaped metal plate, and they're biased to a particular voltage a bit lower than the one before it, so a bit higher with it if you take conventional current and positive to be higher. Anyway, the photon comes in with the photoelectric effect, interacts with the metal, releases some electrons. The electrons get accelerated and smack into another bit of metal, eject some more electrons, and etc. You have a amplification effect with each step in the dynode, and they can have really enormous amplifications, down to the point where a really good one, now this isn't a particularly good one, but a particularly high quality PMT can detect single photon in events. So you're talking about more sensitivity than you really need for this application, although the actual quantum interaction between the particle coming in and the amount of light coming out is quite inefficient. In most cases you still get a lot more than one photon per particle, and the size of the pulse that you get after all of this wonderful electronics, which in itself is a fascinating subject, is generally proportional to the energy of the particle that transited through your detector, and to some degree how well it interacted with your scintillator. So for the purposes of looking at cosmic ray radiation, the best detector is definitely some kind of scintillation detector, because it can not only give you a far more efficient detection, it can also give you an idea of the amount of energy of the particle that was passing through. So if you set a limit on what will trigger your detector fairly high, most of the radiation that's zipping around, background radiation here in the room, is quite low energy, maybe a couple of MeV tops. But if we set that high so that it takes 100 or 1000 MeV to trigger the detector, a great majority of that background radiation just won't be seen, and we can be sure that a far greater percentage of it is actually from cosmic rays. Okay, so let's talk a bit about looking inside things with radiation. It's a pretty common thing nowadays. Medical imaging has made massive use of tomography. The basic idea has been around for a long time, but the mathematics of recovering the data and turning it back into an image was very difficult until we had high-power computers. Essentially, you can think of it like this. If you pass a beam of energy, it doesn't really matter what kind of energy it is, as long as it's penetrating and something that you can focus and tell exactly where it came from, through an object that attenuates that beam linearly, hopefully, although there are ways to deal with it if it scatters it as well. Not harder mathematics, we won't talk about that, but just know that it is possible to recover from diffracting waves as well. But imagine we can move a detector backwards and forwards, and we have a whole bunch of parallel energy, or we can say move something that's generating a high energy beam across. In fact, that again doesn't matter. We can take our radiation from a point source and use a whole bunch of detectors using rays of radiation passing through the object. But okay, ignoring all that, we sweep a detector linearly across and we get some kind of graph of the absorbance that's essentially the shadow of the density or the amount of matter in the object in that direction. If we then rotate, we rotate our equipment a little bit and do it again, and we go all the way around the object, so we get a whole bunch of these different plots from different angles. We get a thing called a sinogram. A sinogram essentially represents the radon projection of the mass distribution in space, or whatever it is you're measuring. It could be magnetic properties, it could be, you know, electric, could be anything. So you've got your sinogram. You then do an inverse radon transform of one form or another. There's a number of different ways to do that. The most common is filtered back projection, because it's relatively simple to understand. There's also expectation maximization methods and a whole bunch of really cool and inventive ways to turn this data set that looks like a bunch of shadows into something that looks actually like what your phantom was to start with. There's a lot of information out there if you're interested. Just have a Google. It's really quite simple, but the mathematics is a bit nasty if you're not used to it. I've been doing a few experiments myself with tomography, particularly capacitance tomography, which has an even nastier problem to solve than simple, say, X-ray tomography like you see in a CT scanner. But this is the basic concept, and for our purposes that's all we really need to know about it at this point. Okay, back here with the tomography, we said that we needed a detector that could, or a transmission system that could produce a beam of radiation, or a detection system that could detect in only one direction, give us some kind of directionality. We need that directionality to resolve the distribution of matter inside the object from various different projections. Beamforming is often done with radiation detection by collimation. You put a big shield around your detector. So if this is your detector, you put in a big block of lead with only a hole here, and you can be fairly confident that the radiation that you're detecting is the stuff that's coming down through that hole, because any other direction it would encounter a sufficient amount of shielding that it would not get to the detector and trigger it. In the case of cosmic rays, as we said, cosmic rays can pass through 4 kilometers of rock. They can easily pass through any practical amount of matter that you might try and shield your detector with, except maybe a planet. So we have to use other methods. The most straightforward method is called coincidence counting. You put two detectors above each other. Now this is a coincidence counter made out of Geiger-Müller tubes. Unfortunately got a bit bent when it was being delivered to me. It still counts though. What essentially you wire up two detectors, one to each tube, and you look for coincidences where a particle triggers this detector and then immediately, or within the light time transition between the two tubes, triggers the other detector. Geiger-Müller tubes actually have a fairly slow response, so the dead time of each detector becomes important, because that gives you ambiguity about whether or not it was actually one particle transiting both tubes, or it just happened to be multiple particles triggering within the particular width of the spike of signal that you get out of the tubes. Again, photomultipliers are much better in that respect, because photomultipliers give you more bandwidth, and the optical system also gives you the ability to have energy discrimination, which allows you to reject a lot of that background radiation that might casually trigger one tube while another bit of background radiation triggers the other tube. This, for example, is a piece of BGO, or bismuth germanate. It's bismuth, germanium and oxygen. It's quite heavy. It's got a density about 7.1. It's taken out of a PET scanner. This is the kind of a scintillator that's good for mid-region MeV, mega electron volt photons. Although particle radiation and other things will make it glow. This would be coupled to a PMT in a PET scanning machine optically, and then any flashes would be read by the PMT and become an electrical signal that you can then do coincidence counting on if you have multiple detectors in some kind of array. So, if we have two counters separated by some distance, and say we have a planet, planet Earth is a pretty good shield. It's obviously more than 4 kilometers thick, so it will give you a way to tell that your radiation came from some cone that is defined by how far apart your detectors are and how physically big they are. This gives you some form of beamforming, but you can do better than that. If you use pixelated detectors, and you can detect the time between triggering one detector layer and triggering a pixel in the next detector layer, then you can not only track that the particle came from roughly this direction, you can tell that it came from some distribution. You can give a much more accurate idea of where the particle came from. As long as you can resolve the time between the two detectors in your electronics, then this also gives you a way to gate for background radiation. It reduces the error in your coincidence counting. Okay, so coincidence counting and scintillators, etc. We've got ways that now we can detect cosmic radiation fairly easily. How would we actually use that if we wanted to image the pyramid? The most straightforward way is to simply build a big array of detectors with a coincidence counting detector, park it alongside the pyramid and wait, basically counting the radiation that you see passing through the pyramid versus radiation that didn't pass through the pyramid. Essentially you see a shadow that the pyramid casts. All the mass inside the pyramid, whatever distribution there is, will produce some kind of image in your detector if you wait long enough. Problem is, it's very slow. To do three-dimensional reconstruction, you need to be able to wheel your detector all the way around the outside of the pyramid. Fortunately, background radiation is essentially isotropic. There is a bit of a change as it has to come through more atmosphere. And obviously the Earth below shields you to some degree, and it'll actually limit how far you can come down and look through the bottom parts of the pyramid. Although the very bottom of the pyramid it was actually built on a small hillock, and you'll probably only be able to image the top half, maybe the top 2/3 of the pyramid easily with this method. But it's very cheap, very simple. It'll just take an awfully long time, and obviously there's another pyramid over here, another pyramid here, and the logistics of it are quite challenging. Another possibly better solution is if you have pairs of detectors on each side of the object that you want to image, say the pyramid. The pairs of detectors, particularly if they can measure the momentum of the particle going in and the momentum of the particle coming out, and they know they have very precise timing so that they can tell that the particle that transited this detector was almost certainly the particle that then transited this detector, and not some other particle that came in and happened to be on a similar path. Then you can quite accurately measure a lot of particles at the same time. So potentially you can use almost all of the flux that happens to pass through your detectors and your object of interest, even if they're not in a direct line. This is a much more powerful technique, and it also gives you an idea about the matter that's in your imaging space, because the amount that they get deflected, the amount that the particles get deflected, is proportional to not only to the density of the matter in here, but also to the atomic number of the matter, because higher atomic number objects tend to scatter more radiation. So given a bit of maths and very good equipment, particularly very good timing and very good energy resolution in your scintillation system, you can get a reasonable idea about what actual atoms scattered your radiation. This has the potential to image the pyramid much more quickly than this system. It's still very slow. We're talking weeks to years to capture all the data. One thing though, this is very hard. It requires much more sophisticated algorithms and computers to recover the data. Not a huge deal nowadays, but the clock distribution between your two sensors that are here separated by maybe a kilometre, and getting all of that data back to your data logging, data acquisition system, and keeping the clock synchronized, a bit of a technical issue. Not a massive one nowadays. It's certainly doable, and there are projects like Fly's Eye and IceCube, things like that have huge arrays of relatively cheap detectors, but using very fast digital acquisition equipment that has all kinds of clever algorithms to distribute the clock throughout the graph of detectors. Very cool stuff. It's definitely doable, and this is a much better approach if you were to do it. The only problem is the size of the detectors. You can see the detector arrays here are, well, the size of the space that you want to image. This is, yeah, impractical. It would cost too much, because you'd simply need a heck of a lot of scintillators. Even if the scintillators are all plastic and you have quite large pixels with only 1 PMT per slab of scintillator, it's going to cost you a lot of money. So, Here's another way maybe to use a similar idea with pixelated detectors with energy momento resolution, but to use smaller ones that you can essentially plonk wherever you like in your space. And it might take a little bit longer, but it also gives you the opportunity to capture particles that travelled in almost any direction. As long as they were deflected by some matter inside the object towards one of your other detectors, you can gain an image over time of the matter distribution in 3 dimensions within the object. In fact, within the complete imaging space, including down into the ground underneath the pyramid. And this technique could be used for other objects, hills, burial grounds. I was just watching a program on, I think it was on Discovery Channel, it might have been on History Channel. Anyway, it was about Chinese emperors and their particular burial grounds. This could be used, volcanoes. I know that there's been a study using muons to image the magma chamber inside a volcano over a long period of time. It used the projection technique that I spoke about first. This one, essentially it looked at the shadow of the mountain over a long period of time with a pixelated detector that was parked there for months, I think. But this particular technique, you could build these devices probably about the size of a telephone booth, maybe a bit bigger, a bit smaller, depending on what your budget is and how many of them you need. I haven't done the math on exactly how many you'd need. It's a function of what kind of matter you've got in here and the amount of scattering, etc. I'm not particularly skilled in the art of this. I'm sure that there are people out there that know a heck of a lot more about cosmic rays and how to detect them and how to track them, that could probably do the math and tell me if I'm smoking crack or not. But it seems to me that if you have these vector momenta detection nodes and you sprinkle them around, as long as you can keep your clock tree and distribute your clock over this network, and you've got really good data acquisition, and you've got one hell of a mathematician that can then write the algorithms to reconstruct your data, you should be able to recover the distribution of matter and maybe even what particular atomic numbers make up the matter inside the imaging space. It's very slow, probably take years, but the pyramid's been there for years. I mean, the pyramid is patient, it will wait for us. It's just a matter of building it and trying it. I think it's practical. I'd like to hear from anyone out there who might have a better idea and perhaps can run the numbers for me and tell me if it is practical. It also has a side effect of being able to do some really cool science at the same time. You have a whole bunch of detectors out there that can detect cosmic rays. If you can build them fairly cheaply, they can do other science experiments while you're there. And it might also tell you something about the, I don't know if you can get isotopic composition, but perhaps you can tell the particular rock that the pyramid is made out of. You might be able to track the construction time based on where we know where the rock came from, so we may be able to work out how it was quarried over what periods of time and things like that. Apart from the possibility of actually imaging the internal structure of the pyramid, which is what this whole thing is about, the possibility of the internal, I think it was, what was it, John Pierre, he had this idea that there might be an internal spiral ramp inside the pyramid, and there was some gravimetric studies that suggested that there was density anomalies that perhaps were consistent with that. This would hopefully fairly quickly tell you whether or not that's completely insane or whether there are actually voids inside the pyramid of any significance. Again, someone has to do the numbers and see how long it would take, but I think maybe only years, or maybe hopefully only months if you have enough detectors. It comes back to the cosmic background radiation, cosmic ray radiation flux. Back here on our graph, the most common rays, and somewhere around this region I think is the rays that will actually make it through the pyramid consistently. They come down about 1 every square meter per second. These really highly energetic ones, you get about 1 every square kilometer per year kind of thing. But the less energetic ones come down like the palm of your hand. There's probably 6 or 7 of them going through it per second, but they're very, very low energy, a lot of them. They might not have even made it through the concrete roof above me. But the moderately energetic ones, every square meter, there's about 1 per second screams through and goes right down into the rock under your feet all the time. So this particular imaging modality sounds fairly practical to me. One thing I know that the American government has looked at using this technology, particularly the Z-based scattering, to detect fissionable materials as one possibility. You essentially, I mean, obviously you can generate a beam of energy like neutrons in particular. Neutrons don't interact with matter because they're not charged very well. So you could scan the entire pyramid with a neutron beam, but obviously neutron activation is an issue, and I don't know if the antiquities people are going to let you get a particle accelerator or a neutron source out there and scan it with radiation. But naturally occurring background radiation gives you essentially a way to illuminate the pyramid at no cost. It's been taking this radiation for eons. This radiation is also obviously responsible for things like radiocarbon production, radiofluorine production, all of the isotopes. I think there's about 70 tons globally in our atmosphere produced per year, like continuously, if you take into account the biological washout of the carbon in the atmosphere plus its production. The total amount of radiocarbon in the atmosphere is about 70 tons, and it's kept fairly constant by the cosmic ray radiation coming in and activating. I think it's a neutron activation reaction that actually produces radiocarbon that we use for radiocarbon dating. But anyway, that's not particularly relevant, but it is interesting to think about uses for these incredibly penetrating rays that come in and can pass through such enormous amounts of rock and give us perhaps details about what's actually inside these things. Anyway, thanks for listening.